So right, let us do some more questions, and these questions are based on the concepts we discussed recently, that is natural frequency, equations of motions, and those things. Okay, yeah, fine. So first question: match the correct answer for the list given below. Okay, so first of all, inertia force. So inertia force means what? Mass into acceleration, right? So I'm into x double dot. Here they're given in terms of y. Okay, you could clearly see they're given in terms of y. Okay, so B. Spring force, it is k into the displacement. Here also again they given in terms of y. Fine. What about damping force? Damping coefficient to velocity, which is 1. And the centrifugal, we know that is r omega square is a centrifugal acceleration. And if I multiply with mass, I will be getting the force. So that is, here it is. So m omega square into r. Okay. So I'm sorry, let me just write it down. Yeah, 3. 2413 is the correct answer. Okay. Moving forward, next question. With the symbol having usual meanings, the single degree of freedom system mx double dot plus cx dot plus kx is equal to f sin omega t represents. This is a very straightforward question. It has a damping. Okay, this system has a damping and also continuous excitation. So what does it mean? It's a forced vibration and also with a damping, which is option C. Yes, moving forward, next question. It's an ISRO question, a very good question. See, it's like a question where you need to just use your logics. Okay, nothing else. Nothing. There is no requirement for explaining this. Simply logic. Okay, simply logic. That's it. Listen, take this mass m. Okay, so first of all, try answering it. Anyways, I won't be able to know whether you are trying or not. Let us proceed. No issues. Okay, so there is a mass m. This mass m has been given a displacement of x. Okay, this mass m has been given a displacement of x. So this displacement x is going to affect this mass and also it is going to affect this spring. But my question is, will this displacement do anything to this C? Will this displacement do anything to the C, that is damper? If your answer is no, then you are completely wrong. See, listen something. Displacement is given to mass, fine. And because of that displacement, the spring is going to get compressed, fine. But note it down that the damping is directly attached to the mass. Okay, so if mass moves in this direction, then damping will also move in this direction. Okay, damping will also move in this direction. So there is going to be something, there is going to be some contribution of this displacement to this damping also, to the mass also, to x also. Okay, fine. But the problem was with this y is given here. Okay, the displacement y was given here. That displacement obviously going to affect my damper. Okay, it's going to affect my damper. Damping force is going to get affected. But what is this y is going to do with m? Okay, so nothing. The displacement y has what is that? No, what I could say, the displacement y has no effect on this mass, also on this spring. Okay, so simply x has effect on all mass, damper and spring, y has effect only on C. So check the options, whichever it is almost matching, that's it. Okay, based on the equation of motion. So obviously first option is wrong because k has been given as x minus y. This is wrong. Second option, no, mass is also having both the components, wrong. And third, mass is having only x component, acceleration, and damping is having both. Okay, x dot minus y dot, that is fine, that is true, okay, because damper has both the effect due to y and also due to x. Okay, and moving forward, k has only x, so obviously this is the correct answer. This is the correct answer. If you check option D, mass has two components, even k has two components, this is wrong. Okay, this is wrong. So correct answer for this question is option C. Okay, right. So next question. Yeah, difference in the potential energies between two arbitrary positions. See, it's a very simple question. Potential energy between two arbitrary positions. X1 is x2 is greater than x1 actually. Okay, so suppose if I consider this is x1, after some times it is getting deflected to some other position x2. Okay, some other position x2. Now obviously x2 is greater than x1. So when it was displaced by an amount of x2, what is going to be my what is that? My potential energy. Potential energy 2. Simply it is 1 by 2 k into x2 square. Okay, potential energy of the spring, right? And what about this? 1 by 2 into k into x1 square. So that is my PE1. Okay, since potential energy 2 is greater than potential energy 1, so subtract PE2 minus PE1. Okay, PE2 minus PE1. So that's going to result in, I can take 1 by 2 k commonly, 1 by 2 take commonly, x2 square minus x1 square. That's it. Check the option. Yeah, here it is. Okay, x2 square minus x1 square. Since I want it to be positive, okay, I'm taking it that. Right, we have one more question based on the spring mass system. In the figure shown, the spring deflects by an amount of delta to a position A when the mass m is kept on it. Okay, see, this delta is the static deflection. Okay, when mass m is kept on it, okay, there was a deflection delta. Okay, at the position A. Now, during the free vibration, the mass is at the position B at some instant. Okay, the mass presently was at position B at some instant. They given that instant was x. Okay, from the static deflection position, the new deflection distance was x. Okay. Now the change in the potential energy, that's what they are asking. Okay, they are asking what is the change in the potential energy. Okay, let us do it. First, let me take question A. Potential energy now, when it comes to potential energy, we need to focus on potential energies of both mass and also the spring. Okay, listen. From the base, okay, let me take this as my reference. Okay, let me take this as my reference. So from reference, I'm sorry. So let us take from reference the distance was h. Okay, from reference the distance was h. So now focus on position A, mass plus spring. Okay, both, because they are asking potential of spring mass system. Okay, they are asking for both. Okay, mass and spring. First, potential energy, right? Potential energy at A, which is equal to, focus on spring. Okay, what's going to be the potential energy? Deflected by delta. So directly I can write 1 by 2 into k delta square. Okay. What will be potential energy of this mass? This mass is placed at a distance h from the reference. I am taking this as my reference. So from the reference, it is placed at a distance h. So the potential energy of that will be mg into h. Okay. So what is going to be? Let me just keep that A there itself. Go for B. Okay. Again, mass plus spring. Okay. Potential energy of B, that will be equal to what? Now what is the deflection? Okay. Now what is the deflection? The deflection now was delta plus x. Okay, so the total deflection will be 1 by 2 into k into delta plus x square. Okay, but what about mgh? That is, what about potential energy of the mass? So the mass was present at this distance, right? What is that distance? See, we know that total distance was h. It has moved by a distance of x. Okay, the distance moved was x. So the balance, this distance will be h minus x. Okay, so that's going to be mg into h minus x. I will just expand it so that will be easy for me. 1 by 2 into delta plus x whole square. Okay, that is delta square plus x square 2 delta x. This will become mgx, sorry, mgh minus mgx. Okay. Again, I'm multiplying inside 1 by 2 k delta square plus 1 by 2 k x square plus 2 will get cancelled, so it becomes k into delta into x plus mgh minus mgx. Okay, and let me take this as equation 2, this is equation 1, subtract 2 minus 1. That is what they are asking. They are asking what is the change in the potential energy, right? They are asking change in the potential energy B minus potential energy A. Okay. Before subtracting, was there any other possibility for me to do any cancellations or not? No, nothing. No problem. Let me directly subtract 2 minus 1. If I subtract 2 minus 1, what's going to happen? If I subtract 2 and 1, what are the things going to get cancelled? See, minus k 1 minus 1 by 2 k delta square. Here 1 by 2 k delta square. So these two will get cancelled. And similarly, mgh and this mgh will get cancelled. Okay. So the balance term 1 by 2 k x square plus k delta x minus mgx. Okay. Listen. For proceeding further, what we know from the basics? At position A, this delta was static deflection, right? So if I draw free body diagram, here I'm going to get spring force, which is going to be k into delta, and there is going to be weight, which is m into g. And we know that under static equilibrium, this m into g and then this k into delta has to be same, because it was initial position, right? It was an equilibrium position. Okay, it was an equilibrium position. Okay, so mg is equal to k delta. Now in place of mg, I can substitute k delta. Okay, what's happening? Check. k delta x minus k delta x getting cancelled. So finally my answer was simply 1 by 2 kx square. Okay, so that is my final answer, which is option. So proceeding to one more question, the equation of motion for a freely vibrating system. Okay, see from this what I can say, what is my equivalent mass, which is 1, coefficient of acceleration 1, right? What is equivalent, what is that, what is equivalent stiffness, coefficient of x, that is 3x, sorry 36 pi square. Okay, 36 pi square. This is my equivalent mass and this is my equivalent stiffness. So what is going to be natural frequency, and they are asking in terms of hertz, so which is equal to 1 by 2 pi root of ke by me. Okay, omega n by 2 pi, right? So 1 by 2 pi root of 36 pi square by 1. So simply take root of 36 pi square and divide it by 2 pi, so which will be 6 pi by 2 pi. So pi gets cancelled, it becomes 3. Okay, 3 and in terms of hertz. Okay, 3 in terms of hertz. Okay, then the correct answer was 3 hertz, which is